Okay, welcome to your Chapter 5 introductory video. As I mentioned for Chapter 4, you guys are going to need to master Lewis structures to be able to grasp Chapter 5. It's used completely to build upon. What we're going to focus on here is bonding theories and really explaining molecular geometry is going to be the focus of this chapter. Learning goal-wise, the main thing you're going to need to be able to do is predict the shapes of molecules. That's the heart of this chapter. We're going to take Lewis structures and build from that. You'll see things like bond angles also covered. I'll mention that. Polarity is actually fairly important, and that's a pretty major topic actually. And then lastly, there's hybridization, which is something that I feel should be reserved for organic chemistry, but we follow the guidelines of the American Chemical Society, and they suggest we cover hybridization Gen Chem 1. So I'm going to give you just a quick little accounting tool of how to do that rather than explaining all the conceptual basis for it. So if you look at this chapter outline, there's a big chunk of this chapter that we are not covering, and you can see that everything in blue we are not covering. So you don't have to worry about the last three sections, and you really don't have to worry much about 5.4 at all. I'm going to, like I said, give you an idea of how to do this. So really focus on reading and studying the first three sections. Okay, so what we're really doing here is applying a concept, a theory called valence shell electron pair repulsion theory. And what this is a model that allows you to predict from the arrangement of electrons around the atom what the shape of the molecule is. And we know that electrons repel each other. They're also going to be attracted to the nuclei of their own atom, but also to other atoms within that molecule. So everything we learned really about atomic orbitals kind of goes out the window. As soon as you bring two atomic orbitals together, everything changes. And that's what some of these theories in this book attempt to address, because you no longer have isolated electrons in an atomic orbital. You now have them attracted to another nucleus that's nearby and repelled by other electrons, which becomes a very complicated situation. And this is just one way we're going to go about dealing with it. So there's two general ideas you have to get out of this VSEPR, and that is electron pair geometry. Some people call it domain. Your book calls it pair geometry, which is fine. And this is really just, very simply, the arrangement of electron pairs around a central atom. They can be bonding, or they could be lone pairs, non-bonding. Doesn't matter. We treat them the same. That's the arrangement of the electrons. You're going to need to learn that to be able to predict molecular geometry and also be able to predict hybridization. But ultimately, what we're after is the true shape of a molecule. And because a pair of lone electrons doesn't really have any sort of significant mass and occupy an actual space, because it's just a probability electron cloud, until it bonds with something and that effectively localizes those electrons, does it give the molecule kind of mass and solid substance. So when we talk about molecular shape, all we really want is the arrangement of the bonding pairs, which results in, obviously, the arrangement of the atoms, because you have to have an atom there to have a bonded pair. Okay, so we have basically 5 different options here for a central atom that we're going to focus on. You can have 2 atoms surrounding it. You can't have 1 because then you don't have a central atom, so we start with 2. You could have 2 surrounding it, 3 surrounding it, 4 surrounding it, 5 surrounding it, and 6 surrounding it. And they have different names. You have to memorize these names. And this is called the steric number. It's the total number. We don't care if it's bonded or a lone pair. It's just a total number. It's what we call the steric number. Now, depending on whether they are bonded or non-bonded, will ultimately determine the molecular shape of the molecule, because we said really for the shape you only care about the bonded. So I'm going to give you some examples here. I'm going to take you also straight into hybridization, which is the end of the chapter, but this all goes together real nice. And this will be a short video because I'm going to do this all in a couple slides here and show you what I mean here. So you do have to memorize these names. These are the base names based on steric number, which is total number electron pairs. You'll also have to learn the names, and that's the biggest challenge for this chapter, for what happens to the shape of the molecule. Because why don't we give you two examples here. Here's two molecules with the exact same electron domain geometry, or electron pair geometry. Okay, so they both have 4 regions surrounding them, correct? It doesn't matter if they're bonded or non-bonded. And you can just circle those regions. 1, 2, 3, 4. 1, 2, 3, 4. Okay, going back up here, so basically they're all tetrahedral. Now this shows you the angles. To space those 4 out equally, and until you get a model kit, it'd be tough to see. I'll try to bring some of those to class. But you space them out equally, and they'll be 109.5 degrees apart. You can see these when you have 3 surrounding. Obviously, 360 divided by 3 is 120. And of course, this is 180. Over here, you get that same 120 because you got 3 around there. We call those equatorial, around kind of like the equator. And then your polar ones, they call these axial. They're going to be 90 from here, but actually 180 apart from each other like that. And then, of course, if you put 2 here and 4 here, this all becomes 90. No matter how you hold it, it looks exactly the same. Because this is obviously 90 right degree angle. There's 4 around this 360, so that's all 90. Of course, the separation between these 2 here is actually 180, but we don't care so much about that because this and this interacts with these before it ever interacts with that. So these 2 both have the same steric number. Oops. Wrong one. This one right here. Tetrahedral, right? So this is their electron pair geometry. However, they have very different molecular geometries. The molecular geometry of this one, now I'm going to draw this as a the bonds as lines here. This is its molecular geometry. This one's molecular geometry is this. So this one is still tetrahedral because it still has the 4 domains around it. So its electron pair geometry and molecular geometry are exactly the same because all the pairs are bonded. Anytime all of the pairs are bonded, the electron pair geometry is the same as the molecular geometry. But this one is known as bent. It's not tetrahedral. So this is tetrahedral. This one is known as bent. Because all we're concerned about is these 2 regions here, because that's the molecular geometry now. And so what you see on the next 2 slides, okay, let me go there. I'm going to come back to this, is basically the tables that you have to memorize for this. And here we are right here. This was the CH4 I just drew. Its electron pair geometry is tetrahedral, and its molecular geometry is tetrahedral. Here is the H2O. Tetrahedral electron pair geometry, but bent or angular molecular geometry. So what's showing you here, number of bonding, number of lone pairs is tetrahedral. This is the one we just did. It could also have 3 bonded and 1 lone pair, and that would give you a trigonal pyramidal shape. And you can see it here. We basically just remove this one here, and you're left with this. Don't think you get this, right? Because you have to start with whatever your electron pair geometry is and basically pull this ball off if you had the stick model there, and you realize you're not going to have trigonal planar. You're going to have this right here, the trigonal pyramidal. And that's what's really important, is starting with your electron pair geometry. Okay? You can see here also, if you start with trigonal planar and you pull one of those off, you also get bent, which is the same as this. You get the exact same thing. In this case, you have only 1 lone pair. In this case, you have 2 lone pairs, but ultimately the shape is the same. The angle, bond angles, will actually be different. And what you see here is, this says less than 120, this one actually being 109.5. This will depend on the attached molecules, but it will not be as small as 109.5 because those lone pairs of electrons, they actually take up space and they push these 2 downward. And that's what happens. So the angle is less than the 109.5. It starts at 1 and 9.5, but when you put lone pairs up here, it makes it slightly less because lone pairs are not held by multiple nuclei, only by one nuclei, and therefore they take up much more space, is ultimately what it comes down to. This table continues now to the other two. We said there was a Sn equals, we didn't bother with 2 because that's always linear, obviously. We started with 3 as far as our table. So there'll be four in the table. But now you can see as you get to these two, there's a lot more options. You can have 4 and 1, 3 and 2, and 2 and 3. And for 6, got a couple down here we won't deal with much. And your book doesn't talk about it, so we won't deal with it all. So really you just have to worry about these 4, 2, 5, 1, and 6, 0. And of course the first one is always the same thing. And you see some of them have odd shaped names. Seesaw, and this actually looks like a seesaw, and you could actually see it in your hand. You'd realize that. You got T-shaped. This one winds up being linear. Your octahedral becomes a square pyramidal. You've got a square along this base here, and then it comes up to a pyramid. And then you've got square planar. It's all in one plane. So those just need to be memorized. Now, the next thing that happens in the chapter is to say, okay, what's the hybridization? And when we talk about hybridization, we really mean, you could talk about the hybridization of the molecule, but we really mean the atom within the molecule. So we're going to go back to these two again. And both of these, remember, have the same electron domain geometry and the electron pair geometry, and therefore basically they have the same hybridization. Hybridization is based on the electron domain geometry. And I'm going to go through this a tiny bit in class, give you one example. It's in your book, but you're not responsible for my class other than to be able to tell me what the hybridization is. You don't have to understand how it comes about. And really it's kind of just a model for us to grasp what we can't see actually happening. So what people do is talk about the combining of atomic orbitals and ultimately getting new orbitals, what we call more molecular orbitals now. But the easy way to do this is simply like this. Count the regions surrounding. 2, 3, 4. 1, 2, 3, 4. Therefore, these two will have the exact same hybridization. Knowing that atoms can have at most one s orbital. You learned that in chapter 3, right? And three p orbitals. This is what you use to build your hybridization. What we're doing is talking about the hybridization of the carbon, the central atom, of the carbon here, of the oxygen here. You simply count the regions. So you got 4 regions surrounding it, okay? So the most you can have is an s. That's all we ever start with is one s orbital, and 3p. So this is the hybridization of both the oxygen in water and the carbon in methane. They are exactly the same. You simply count your regions. So let's go back now and say, okay, what's the hybridization, for example? Oh, let's look at examples here. Here we go. Down here. Hybridizations here. They don't give... Okay, so carbon dioxide. Let's just do this carbon dioxide here. What's the hybridization on carbon dioxide? Well, there's only 2 regions. You can have one S, and the rest has to be occupied by P. So basically it's sp hybridization because you have 2 regions. 1, 2. Here you had 4 regions. 4. So your options are basically sp, sp2, sp3, and then we get into using d orbitals because you're going to need to do that for these guys here that have 5 and 6 regions. So you wind up with, right here you see it, sp, sp2, sp3, sp3d, sp3d2. And that's what it's showing you. It doesn't matter if they're bonded or non-bonded for hybridization. So all you have to do is recognize these notations and simply count the regions around the central atom, and you have what you need to be able to answer any hybridization questions for now. We'll leave the conceptual theory stuff to organic chemistry. So the last thing then for this chapter is to talk about molecules' polarity, okay? And we saw differences in electronegativity discussed in previous chapters. So what we have here is the possibility that two atoms bound together in a molecule will have differences in electronegativity, resulting in an unequal distribution of the electrons in that bonded pair, which gives us what we call a permanent dipole. Okay, so let's take an example now. Oxygen is much more electronegative than carbon, so effectively this winds up with what we call a partial negative charge, and that's the notation for it, and this would wind up with a partial positive charge, and this would have a partial negative charge. And another way of notating it, the positive's over here, and the electrons are pulled in this direction. So this molecule has polar bonds, but the molecule itself is nonpolar. It has no dipole moment, and that's because think of this like a tug of war. They simply cancel each other out. Ultimately, there is no pole. Okay? Same here. It's tougher to see. If you took physics, you might know something about vectors, but all four of these cancel each other out. Ultimately, this becomes nonpolar. To be polar, you can't be symmetrical. Okay? Things can't cancel out. You look at water. This has a net dipole. Some people put it up here, but net dipole in this direction because they do not cancel out. That's due to the higher electronegativity of oxygen over hydrogen. So this molecule is polar. And ultimately, I can give you a list of shapes that are symmetrical. So if all the attached atoms are identical and it has one of these shapes, it is nonpolar because these are symmetrical. However, let's take carbon tetrachloride. This is polar because it's no longer carbon tetrachloride. It has one chlorine, and we're going to have a slight dipole in this direction because chlorine's more electronegative. We don't cancel out anymore because hydrogen isn't electronegative enough to cancel out with this chlorine. So we do have here a slightly polar molecule. And that's simply because not all the attached atoms are identical. So that's the other major thing to get down in this chapter. And here you see just some dipole moments to give you an idea. They use units of Debye, but you don't have to worry about that. This is a pretty polar molecule, and this is a slightly polar molecule. And that's something you just need to get familiar with and start to looking at shapes of molecules. And that'll be important for you to master VSEPR and molecular geometry to be able to predict polarity. And that concludes the video.